Hi, welcome to this screencast on Chapter 9D, Binary Operations. And before we embark on binary operations, first a brief review. We have been talking about set theory and in the meantime discovered that set theory really forms the basis for the mathematics as we know it. Cardinal numbers, for instance, formed the basis to really for the first time talk in an exact way about infinity, and for instance to determine whether the number of points on a line is more or equal to the number of points in a plane. And again, we talked about relation between two sets, or the elements of sets, which forms the basis for the idea of a function. And now we move on to binary operation, which of course forms the basis for operations as we know them, like addition, subtraction, and so on. Now, having said that, first of all, what is really the definition? Now, not surprisingly, I start with a set, like for instance the set n. And I have my elements 0, 1, 2, 3, etc. And of course here I have also another set, also n. Now with also all the elements we know from this set. And instead of connecting one element from the domain to another element in the codomain, I take two. For instance, the numbers 1 and 2, and I perform an operation on these two numbers, giving of course the answer 3 being an element of n again. Now in this case we see that the result of the operation is again an element of n, and therefore we say that addition is a closed operation, whereas for instance if I look at subtraction, this leads to an element which is not of n, and therefore it is not closed. Which leads me to the subject of closure. Of course, an operation, a binary operation, doesn't need to be an addition. It can mean any operation, so therefore we use a general symbol star. And an operation could for instance be A star B equals A plus 2B minus 3. And if I define this operation in the set Z, well, let's have a look if this then would be a closed operation or not. Well, I'll take an example. I have for instance 2 star negative 10, and then obviously it is, the answer is this, being negative 21. And you see negative 21 is an element of set, so therefore this is a closed operation because it is easily seen that this is true for every A and B. We could say that in this case Z is closed under this binary operation because of what we just saw now. Or another way to say it is that a closed binary operation is indeed a function in this time. Now that was my phone, so I have to start over again. So we could say that a closed binary operation has as a domain the cardinal multiplication, because A and B are from Z, and the codomain is then Z again. Now I would like to have a look at the different laws for these operations, or sometimes they don't apply, like the associative law, the commutative law, and the distributive law. Okay, the associate law is really very easy because to give you a very easy example, 2 times 3 times 4, well, it doesn't matter if I first calculate 2 times 3, which is of course 6 times 4 is 24, or if I first calculate 3 times 4, which is 12 times 2 is 24 as well. In this case, this operation multiplication is obeying the associative law. Or in general, if I have A star B star C, where A star B is calculated first, and when that is equal to A star B star C between brackets, then this operation obeys the associative law. The commutative law is very simple, the situation that if I have 3 plus 5, it is the same as 5 plus 3. Obviously this is true for multiplication and addition, but it is not true, as you know, for the operation subtraction. Okay, so the question is now, why would these laws be relevant? Now, if I have a star operation which obeys the associative law, and I have a long, this must be stars, sequence of this operation, then the order in which it is performed, it doesn't matter. So I simply leave the brackets, and therefore it gives me the opportunity to write this short as a to the power 5. And all other laws we know from the powers are applying. So a to the power 5 star a to the power 3 equals a to the power 8. Remember, I'm not multiplying, I have here a star operation. Now, in case both laws apply, associative and commutative law, in operation, then even this law we know already from the powers applies, that if I have a star b squared, what I do in fact have is a star b star a star b, and since it is associative, I can leave the brackets, so it is a star b star a star b, and again I can say, okay, it doesn't matter, so I calculate this first, and because the commutative law applies as well, and that was the presumption in this case, I can swap those b and a between brackets, leave the brackets alone again, and say in the end that this equals a squared times star b squared. Now this is only true if both laws apply. If they don't apply, we can't work like this. Now, to give you an example for the distributive law, I could say that multiplication is distributive over the addition. To give you an example, if I have 10 times 5 plus 3, I can write this like 10 times 5 plus 10 times 3. And of course both are 80. Now to apply this generally, if I have a star operation like A star B equal A plus 2B, and I have a circle operation A circle B equals 2AB, then let's have a look if this operation obeys the distributive law. And then I can say, for instance, that if I have A star B circle C, is this then equal to A star B circle A star C? Now let's have a look. The circle is 2AB, so I get here A times, and then instead of A and B I have B and C, so this is 2BC, which leads to the following conclusion, that this equals A plus, and instead of B I have 2BC, which is multiplied by 2, so this gives me 4BC. On the other hand, here I have A star B, which gives me A plus 2B circle A plus 2C, which then leads to, if I apply the circle operation, 2 times A times B becomes then 2 times A plus 2B times A plus 2C. And obviously these two are not equal, so in this case the distributive law does not apply.